Hello, PreCalculus. Welcome to section 2.1.2. We're going to do a little bit more graphing of radical functions. So we're going to take our radical function that looks like this guy over here, and we're going to put it into exponential form, so it's more like the power functions that we were looking at last night and today in class. So, looking at this first one here, this is the same thing as 2 times 5x cubed to the 1/4 power, right? So remember, this guy is like to the first power, and then the part that's in the radical is what goes down here. So this would be 2 times 5x cubed to the 1/4 power. I could expand that out a little bit and say 2 times 5 to the 1/4 times x to the 3/4. And so the shape of my graph should look something like this guy. Now it's getting a little bit stretched right here, so it's going to be a little bit bigger, but I should have the shape of x to the 3/4. So x to the 3/4, remember this is x to the 1 power, right? And then this is x to the 1/2 power. We want something kind of in there like that, but because it's getting stretched up a little bit, I think it's really going to be probably closer to something more like that because of the stretch. But notice it still has a slight concave down piece to it, just like a square root would, right? Well, that's not quite right. Square roots are more like that. It's got that concave down nature, and that's what we're looking at. We can test it out on Desmos. So we really want 2 times 5x cubed to the 1/4. Come over here. I want 2 times 5x cubed to the 1/4 power. Oh, that is not what I wanted to write at all. 5x cubed, close your parentheses, Miss Harris, one more time. No, that's not me. How about there? No. 5x cubed, close up parentheses. Come out of there. Close the second parentheses. Sorry about that. Raised to the 1/4. The 1/4, no. Yeah. 1/4 power. I'm all kind of discombobulated now. There's a tropical storm coming too. Did you see that? All right, let's see if I can get this right. Huh? I think we're there. All right, notice here, it looks, here would be the line. I can't draw it. Oh, I wish I could draw it. But there would be a line in here. My x is bigger than y equals x, which would go through this point here. Oh, you can see that. That point would go through that point. That's y equals x. So it's bigger than that, but it's still got the concave down nature that a square root function would have. So even though it got stretched vertically, it's still got that concaveness to it where it's slightly curved down. All right, so this is kind of what we're looking at here. What's the domain of this guy? From 0 to infinity, there is a point here, so we're going to include that 0. Range is also 0 to infinity for that guy. All right, where are my x and y intercepts? They are the same for this one. And that is right there at the origin, 0, 0. End behavior. What is the limit of this guy as x goes to negative infinity? Well, does x go to negative infinity? No, my graph stops right there at 0. So this does not exist because x doesn't go to negative infinity. If I wrote positive infinity, I meant negative infinity. What about the limit as x goes to positive infinity? So as x goes to positive infinity, my y's are going up to positive infinity. Is this guy a continuous graph? No. It is once it gets started here, right? If I start my graph here and I keep going, it is continuous. So it's not continuous on all real numbers, but it is continuous on its entire domain. So we want to say continuous on 0 to infinity. In other words, it doesn't have holes or asymptotes. Is it increasing or decreasing or a mixture? This guy, when I start drawing it, is always increasing. So we're increasing also on the entire domain. Except for what can't I include for increasing? 0, right? Because at 0, we can't say we're either increasing or decreasing. It's a none of the above. Where are we decreasing? Never, right? It's always increasing, so no decreasing intervals. And then, is it even or odd? Well, this guy does not have symmetry, so neither even or odd. I'm just going to write neither this way, so I leave room for B. All right, look at B. Let's first put it in exponential form to see if we can figure out what is the shape of this graph. This would be 6x minus 8 to the 1/5 power. Now this one's a little bit harder than the ones we're doing in class. The reason being is this one has what? What is different about this one than all the other ones that we did in class? Hopefully you see that all the other ones in class did not have a transformation. This one is actually getting shifted to the right. Now it's to the 1/5 power. What should that look like? It should be looking kind of like our cube root, which would normally go through 0, 0, but this guy got shifted to the right. So this guy is actually going to go, maybe, look something like that, right? Because of that shift in there, this is not one where I'd ask you to find like an x-intercept or a y-intercept. You can find them by hand. We can find the x-intercept by hand. The y is a little bit harder, but let's look at it on the graph. Desmos will tell us what's the domain of this guy? It's cube root, so it's going to be negative infinity to positive infinity. Same thing for our range. Our x-intercept and y-intercept, I'm going to rely on my calculator for this one. I don't think they'd ask you anything quite this challenging on the SAT. Like I said, you can find the x-intercept by hand. Finding the y-intercept is much more challenging. Let's see. That was 1/4 times 6x minus 8 to the, oh my goodness. I'm out of a fraction. All right, times 6x minus 8 to the 1/5 power. All right, and notice this guy got shifted a little bit, right? We can find that x-intercept. It's not too hard algebraically. Look at that y-intercept there, negative 0.379. That's hard to find algebraically. You could, but if this were to be on your test, it would probably be multiple choice. Not multiple choice. It would probably be on a calculator portion. So the other one is negative 0.379. All right, looking at our graph, what's the end behavior? We can do this one. The limit as x goes to negative infinity of g of x. It looks like it's going to kind of peter off here, but it doesn't. So as x goes to negative infinity, I don't have an asymptote stopping it. So eventually, if I go out far enough, it'll get down to negative infinity. Likewise, the limit as x goes to positive infinity, it's going to go out and up. Eventually, it'll get to positive infinity for your y's. This graph, when I draw it, is always increasing. I'm always getting bigger and bigger and bigger as I go left to right. So we're increasing on all of the domain, which is negative infinity to infinity, which means we're never decreasing. Does it have any... Is it an even or an odd function? Does it have symmetry there? No, because it got shifted away from the origin. It's no longer symmetrical about the origin. So this one is neither even or odd. All right, go ahead and pause your video. See if you can figure out what does h of x look like. Check it on Desmos, and then come back. All right, here we go, h of x. The first thing I want to do is I want to put it in, oops, I need a negative sign, exponential form. So 12x squared minus 5 to the 1/3. My knee-jerk reaction is to say, oh, it's a cubic. It should look something like this. Except for it's got a shift, right? So it's going to be more, I think, more like this. That got shifted to the right. My problem is that's not x minus 5 in there. There's x squared. So I really think it's going to treat the overall graph to more of a 2/3 feel to it. which makes me feel like maybe this piece here is going to do something like that. I really don't know, to be 100% honest. So let's go check it out in Desmos. Oh, you already did, didn't you? So we're going to put in negative. First of all, negative. Oh, and then the reflection from that negative sign. I didn't even take that into account. So maybe this whole thing gets flipped down like that. I don't know. So we got negative, in parentheses, 12x squared minus 5. Okay. And then we're going to raise that to the 1/3 power. Woo! I wasn't expecting that one. That is really cool. So I was thinking maybe something like this. 12x squared minus 5 to the 1/3 power. I think I got it all in there right. Look at that pretty thing. Negative 12x squared minus 5 to the 1/3 power. That's it. Didn't even come close, did I? Kind of have the right idea, but not really. That looks really cool. So looking at this graph, why is that saying that's 0, 0? That's not 0, 0. There you go. Those are our points of interest. Looking at this graph, what does it look like the domain and the range of this guy is? This is, by the way, this is not something I expect you to be able to graph this guy by hand for sure. It's got a lot of stuff happening. So domain for this guy would be from negative infinity to positive infinity. What's the range of it? Looks like we're starting here at negative infinity. My highest y value is up here at 1.71. So my range goes from negative infinity up to 1.71. My x-intercepts, it looks like we have 2 of them. Which here's a question for you. Does that make this a 1-to-1 function? Hopefully you said no. This guy would not have an inverse because it doesn't pass the horizontal line test. We have 2 x-intercepts, for instance. One is at negative 0.645 and one's at 6.645. So negative 0.645, one at 0.645. Where's my y-intercept? That was that high point on the graph, which was up at 1.71. Can we take limits? Can we find end behavior of this? We sure can. What does it look like is happening to our graph of h of x as we go to negative infinity and positive infinity? I'm having a hard time drawing my negative signs today. Looking at our graph, it looks in both cases that we're going to go down to negative infinity. So our y's are going to negative infinity both sides of our graph. All right, is this guy increasing? Oh, is it continuous? Well, it sure seems to be continuous. I might question it up here, but I definitely have a point up there, right? So I really think we're continuous on the whole thing. So continuous on negative infinity to positive infinity. And we do have an increasing portion and a decreasing. So we are getting bigger as I go from negative infinity up to 0. At 0, it turns and comes back down and starts getting decreasing from 0 to infinity. So we're increasing, negative infinity to 0, don't include that 0, decreasing, 0 to infinity. All right, what about this? Is it even, odd, none of the above? Hopefully you can tell by those x-intercepts, it is symmetrical about the y-axis. So this is an even function. It is so pretty, I really like it. This is an even function. Okay, just to recap, should you be able to graph this particular one by hand? Absolutely not. We want to get the general shape of some of the monomials, which means it's x to some power. Those kind of power functions, yes. Something as advanced as this, where we've got shifts and squares in there, nope. We're going to plug this guy into Desmos and call it a day. So that's it for this. Come back. Video 2 is going to be solving square root and cube root and fifth root equations.